We've explored the relationship between position, velocity, and acceleration for scalar valued functions. So now we're going to expand those ideas and look at position, velocity, and acceleration for vector valued functions in three-dimensional spaces. We know that we can use vector valued functions to describe motion in space. Velocity and acceleration are going to capture how that motion changes. The relationship between position, velocity, and acceleration is the same one that we've worked with in two-dimensional spaces. If our position is given by the vector valued function r of t equals x of t, y of t, z of t, then we know that velocity is going to be the derivative of that position function, which is going to create a new velocity vector. Similarly, acceleration is going to be the vector given by the derivative velocity, or the second derivative of the position function. The velocity vector is going to point in the direction of motion at any particular time t. The magnitude of that vector then gives the speed. Acceleration, as always, measures change in the velocity. All right, so given the position vector r of t equals t squared, t cubed, we're going to find velocity and acceleration. So velocity is going to be the vector 1, 2t, 3t squared. And acceleration is going to be the derivative of that, which is going to be the vector 0, 2, 6t. If we wanted to, we could also calculate the speed, which is the magnitude of the velocity. So that's going to be the square root of 1 squared plus 4t squared plus 9t to the fourth. I don't need to write that one as squared. And that would allow us then to compute the velocity, acceleration, and speed of this object as it moves along the curve at any time t. Our next example is pretty similar, but we're working in two-dimensional space, so we have the vector valued function 5 minus 3t, 2 plus t, and we want to find the velocity and speed, as well as the acceleration of the object. So for part A, the velocity is going to be the derivative of the position function, so we're going to get negative 3 and 1. And the acceleration, the speed is the magnitude of the velocity, so that is going to be the square root of 9 plus 1, or the square root of 10. So this thing is moving at the same speed. Its velocity is direction dependent. And then the acceleration is the derivative of velocity, but since the velocity is a constant vector, the acceleration is going to be 0. All right, this time we're going to go the other direction. We have an acceleration vector. This is our acceleration vector right here. And then we also have an initial velocity. And we have this initial position. So we want to find velocity and position vectors that satisfy those initial conditions. All right, so we know that velocity is going to be the antiderivative of the acceleration vector, which we can do piecewise, and that's going to give us t and negative 2t plus our constant vector. But the velocity at 0, plugging 0 in for t, we get that 0, 0 plus c1, c2, which tells us that c1, c2 must be equal to our initial velocity, which is negative 1, 4. And so we can write our velocity vector as the vector t minus 1, negative 2t plus 4. From there, we know that our position vector is the antiderivative of our velocity vector, which is going to be anti-differentiating t minus 1. We get t squared over 2 minus t. And then we get negative t squared plus 4t. And of course, we still need our constants. our position at 0 is going to be plugging 0 in for all of our t's. We get 0, 0 plus c1, c2. So again, we see that c1, c2 must be equal to our initial position, which is 3, negative 2. And so our final position vector is going to be the vector t squared over 2 minus t plus 3, negative t squared plus 4t minus 2. All right, summarizing our big ideas. We know that position gives the location along a curve. Velocity gives us the direction that we're moving along with the speed, because speed is going to be the absolute value of velocity, but the velocity itself captures our direction. Acceleration measures the changes in our motion. In particular, it's going to measure the changes in our velocity so that a vector and a vector valued function, we can use all of these ideas together to describe motion completely along a particular curve.